Hello, everyone. Welcome back. We are going to pick up where we left off last time, which was introducing kind of the nuts and bolts of algebraic fields. And then hopefully I will give you the payoff today of how all of this allows us to design and use multi-error correcting codes. So that's the idea of where we're going. Before I launch into my diatribe, do you have any questions? All right, so I'm going to continue working on the whiteboard for now, but I hope that by the end of today, we will get back onto the note set. Okay, so let's start with recall that an algebraic field is a set of symbols where the symbols plus, minus, times, and divide by, quote unquote, make sense. So adding and multiplying, they're usually the easier ones to establish. The existence of subtraction and the existence of division are usually a little bit harder. So to help make sense of those, I alluded to the two of the, I think 7 or 9 field axioms. So the highlights from what are called the field axioms are that in order to be a field, an additive inverse must exist. So additive inverse must exist. And an additive inverse is a very fancy way of saying you can always take a number in the field and add it to some other thing in the field and get 0. Which by extension actually means that 0 must always be in the field. The other is the axiom of a multiplicative inverse. And we only require the multiplicative inverse to exist for all non-zero field symbols, or field elements, if you like. We don't require there to be a number that when you multiply it by 0, you get 1. But for everything else in the field, in order to be a field, you need to be able to multiply by something else in the field and get to 1, which by extension means that 1 always has to be in the field. So at the very least, if you have a field, you're guaranteed a 0 element and you're guaranteed a what we call a unity element. Normally you just call those 0s and 1. Okay, so we ran through a couple of the more basic finite fields. And a finite field is simply a field with a finite number of members. So we established among the list of finite fields the integers mod 2, that worked out to be a field. The integers mod 3, that worked out to be a field, because we showed that both of these fields possess additive inverses and multiplicative inverses. But when we got to the integers mod 4, this did not meet the requirements. So the general result of this pattern, if you like, is, so you can ... this, but the end of the story is that the integers mod p is a field if p is prime. So if you're doing modular arithmetic, then you are guaranteed the field axioms to hold if your modulo number is a prime integer. So that kind of leaves a hole, if you like. So we have z2, z3, z5, z7, All of these are finite fields in which we don't need to really look outside the range of integers. But I am going to propose a field with 4 elements, right? Because the reason that this is a problem is this field has size 2, in that there are 2 elements of the integers mod 2. This has size 3, and this has size p. But I would really like to have a field with size 4, or size 8, or size 16. None of these are prime numbers, but they would all be really nice to build codes off of, because they would mean that I could map the field elements to bits and bytes and all that stuff. So I want, this leaves a hole in my pattern, and the hole is actually exactly where I want things to be. This means we can design a ternary code, right? A code based on integers mod 3, but you would need a computer that had, what is it? Is there such a thing as ternary bits? Tert? No, never mind. I'm not going to go there. So I propose a finite field with 4 elements. And it gets back to our polynomial friends from earlier in this module. So my proposal is the set of polynomials whose coefficients are binary, defined over the variable x, modulo x squared plus x plus 1. Okay, so to review, this is all polynomials in the variable x with coefficients that are either 0 or 1. And then this is our symbol for modulo. And then this thing is what I'm treating as the new 0, or the wraparound point, if you like. Okay, so first things first, before we establish that this could be a field at all, does it have 4 elements? So I think the best way to do this is just to list the 4 elements. So let's start with all the polynomials that belong to this set. Well, there's the 0 polynomial. There's the 1 polynomial. There's x plus 0. There's x plus 1. And I think the next thing would be maybe x squared. But we know that x squared is equivalent to minus x minus 1, which is in this space equivalent to x plus 1. So this and this are equivalent. And I think you can keep doing that if you build up any more members of this list. All of them are going to be, triple equal sign equivalent to an earlier member in the list. Okay. So these are the members, or the symbols in this field, which I haven't actually proved as a field. Right now it's just a collection of 4 things. Okay, so let's go through an exercise and try to find the additive and multiplicative inverses of each of these elements. So, and this actually might be good exercise if we want to open it up to the crowd. So who wants to help me find the additive inverse of 0? We'll start with the easiest one.
Just 0.
Yeah, what do I add to 0 to get 0? 0. How about the additive inverse of 1?
X squared plus x.
Okay, but we're looking for something in the field.
Oh, yeah.
Yeah. what do I add to 1 in this with this arithmetic rules to get to 0? If I add 1 to 1, I get 2. But remember, we're living with coefficients mod 2. And so this is the other kind of modulo you have to look out for, is that whenever your coefficients wrap above 1, they wrap back to 0. So 1 plus 1 is 2, but 2 is equivalent to 0 in this world. What would I add to x to get to 0? Have I abstracted away from everyone now?
Is it x?
It is. If I add over here, if I add x to x, then I get 2x. No one's going to fight me on that. But remember, 2 is equivalent to 0. So I get 0x. In the chat, so Jack's lucky I didn't look at his chat. And so I think you're seeing a pattern, actually, that in this particular field, if I add anything to itself, then I get to 0, because all of the coefficients are mod 2. Right. This is our XOR. Okay. So let's try something that I think is a little harder, and that is multiplicative inverses. Remember, we don't need 1 for 0, so I won't ask you that. Here's the easy one. What's the multiplicative inverse of 1?
1.
Yes. What do I multiply 1 by to get 1? 1. Good. How about x? What do I multiply x by to get back to 1?
X plus 1?
Let's try it. So x times x plus 1 gives me x squared plus x, but x squared is equivalent to negative x minus 1. Drop down the x. It's looking good. The minus x and the plus x cancel. I get minus 1, which is equivalent to 1. Awesome.
That was just a lucky guess.
You didn't have to say that. Oh, I mean, we all knew it based on the rising pitch at the end. X plus 1? Okay, so let's see. Does it follow that if x plus 1 is the multiplicative inverse of x, that x is the multiplicative inverse of x plus 1?
Yes.
Good. Yeah, because one of the field axioms actually is that multiplication is commutative. And you would want that to be true because there's no reason that I couldn't just write the x over there in this little exercise and I get the same answer. Good job, Jack. I got you. Okay, so I think, I've ignored many of the other field axioms, but they do all hold. And so what we've shown is that we have found a set of 4 things over which plus, minus, times, and division makes sense. And they all have their necessary inverses. And so this is what I'm going to call the finite field of size 4. Okay, so all we had to do really is get outside the realm of integers. And if we enter the realm of these particular polynomials, modulo this particular polynomial, then all of a sudden we get the things we need to be a field of size 4. And this is why the mathematicians call these a set of symbols rather than numbers. It's because the field itself can be populated by any things over which these operations make sense. It doesn't have to be numbers. In particular, it can be objects like polynomials. But what it also means, and one of the consequences of this definition of a field, is that, I mean, the members are 0, 1, x, and x plus 1, but that's only because of how we built up like a familiarity with these particular symbols. Right, I guess the flippant way of saying this is that the field of size 2, which we've established is the integers mod 2, which is a set 0, 1 with plus and minus and times and division regularly applied. There's nothing forcing us to call this 0, 1, 1. It could be hamburger and hot dog. Right? It's just whatever. It's two things. And as long as I define what hamburger plus hot dog is, and hot dog plus hot dog, and et cetera, then I have a field. Okay, so this is why it's called abstract algebra. It's because the fact that they're numbers or integers actually doesn't play a role. It's properties of these things that we're interested in. Okay, so if there's one thing you're going to leave this class with, it's the fact that you can communicate over the space of hot dogs and hamburgers. I'm convinced. All right, questions so far?
First it's the lollipops, now it's the hamburger.
Am I food fixated? Is that my problem? Don't answer that. All right. So that was a field of size 4. And I'm going to do one more example just to show you that it can go get bigger. Let's think about the polynomials defined over the first 3 integers, 0, 1, 2. So this is another example. But we're doing these modulo x squared plus 1. Okay, so let's work out the members of this set. 0, 1, 2, because we're doing the integers mod 3 here. And then x, x plus 1, x plus 2. And then 2x, 2x plus 1, and 2x plus 2. Anything beyond here, and we get an x squared, which then is equivalent to 1, or negative 1, sorry, which is equivalent to 2 in this space. Okay, stop. Okay, so I'm going to try, and I don't know how well advised this is, but I am going to open up the whiteboard to the class, and I would like you all to help me identify the additive inverses and the multiplicative inverses of these members. Now, I've never done this before, and I actually don't even know if you all can draw on my whiteboard. Oh, you've actually been refraining from graffitiing me this whole time. Oh boy, here we go.
If you think yours is really bad.
All right, someone's got 0. Good.
Okay.
So remember what the definition of an additive inverse is. It's for every member of the field, there exists another member of the field such that A plus B equals 0. Right, so this is the definition of an additive inverse. There we go. Oh, I don't want to use x because x is one of our x is one of our symbols. I'll scratch it out. Good so far. Ross and Ethan are racing down the additive inverses. Anyone want to contribute to the multiplicatives?
You got the memo on the last one?
Yeah, let's call that x plus 1. So if you need table lines, let's do that. Okay, so x minus 1, I'm just going to translate that. Minus 1 is equivalent to plus 2 in the integers mod 3. So yeah, x minus 1 is equivalent to what Andrew's going to write here. No, what I'm going to write here, x plus 2. Good. Uh-oh, we've slowed down. Good. If x plus 2 is the inverse of x plus 1, then x plus 1 has to be the inverse of x plus 2. Good. This one's wrong. So it's not, if that was meant to be a 1, that's not true. So let's check x times x, call that x squared, which is equivalent to negative 1, which is equivalent to 2, because we're doing ternary arithmetic. But you're close. So if we do x multiplied by x plus 1, then we get x squared plus x. The x squared is equivalent to negative 1 plus x. And this x minus 1 is equivalent to x plus 2, which is not equivalent to 1. So this is a frowny face. This is also a frowny face. There we go. So x multiplied by 2x gives us 2x squared, which is equivalent to 2 times negative 1, which equals negative 2, which is equivalent to 1. Happy face. Good. Well, by process of elimination, the bottom two are either their own multiplicative inverses or they have to be a pair. Like, Hey, teamwork, nice work. Smiley face. Okay. Nice work. Thank you to those of you who participated. And oh. Okay. What have I done? I think what we just established is that there are 3, 6, 9 members of this field, and it is in fact a field. So this it earns the name, the finite field with 9 elements, so F9. Okay, so I think we've established that that you can populate these non-prime sized fields if you look outside integers into the realm of polynomials. And this is in general a way to do it for f sub q, where q is not prime or q is composite, is you can find these fields if you look into the polynomials modulo a irreducible polynomial. So the whole idea is that this worked because this is irreducible in the parent field, right? Because this polynomial x squared plus 1 acts like a prime number in Z3 of x. Okay. So let's talk about the last kind of introductory topic here, and that is the notion of primitive elements of a field. Okay, so just to review, the finite field of size 4 comprises 0, 1, x, and x plus 1. In truth, it's hot dog, hamburger, ice cream cone, and popsicle, but the names we give them doesn't matter as long as we know the operations. These polynomials have familiar operations, so that's why I'm going to keep writing them as polynomials, but they don't have to represent polynomials. They're just 4 things with these operations defined on them. And what I'd like to do is I would like to replace this symbol with this symbol and convince you that that means that this one is alpha squared. Right, so remember that F4 can be thought of as the polynomials with coefficients mod 2 modulo the polynomial x squared plus x plus 1. So that means that alpha squared equals x squared equals negative x minus 1, sorry, is equivalent to, which is equivalent to x plus 1. Okay. And then what do you think is going to happen to alpha to the 3? Does anyone have any intuition on this? Like we can work it out, and we will.
Would it go back to 0?
Close. It won't go back to 0. It'll go back to 1. Right? Because when you're multiplying, we should never end at 0, because then we'll never get away. But we do get this ring property, where when we multiply, we go around the ring, and we come back to where we started. So alpha to the 3 is what? X plus 1 times x. Well, let's do it. Let's do it the real way. Real way, whatever. We're talking about hot dogs and hamburgers. There's nothing real. X to the 3, and this is what? X squared times x, which is negative x minus 1, sorry, equivalent to negative x minus 1 times x, which is equivalent to x squared plus x, which is equivalent to negative 1, which is equivalent to 1. Okay, so alpha to the 3 actually brings us back to here. And so this is our first introduction to the property of rings in fields, is that when you multiply, and technically, well, let's just focus on multiplication, that when you keep multiplying a primitive element by itself, you actually end up hitting all of the non-zero elements in the field. And if you do it enough times, you get back to 1. Okay, so let's try that again with the, I don't know if we've actually covered this one. This is the finite field of size 8. We did F9, but let's do the finite field of size 8, which is, or which can be thought of as the polynomials with binary coefficients modulo x to the 3 plus x plus 1. Okay, so I'll save you the trouble. The elements of this field are 0, 1, x, x plus 1, x squared plus 1, x squared plus x, and then x squared plus x plus 1. So let's start by renaming this element alpha. And if I were to square alpha, where do I land? Or do I land on another field element? It's right there, x squared. The harder one is alpha to the 3. So alpha to the 3 is x to the 3, which is equivalent to, according to this mapping, negative x minus 1, which is equivalent to x plus 1 because we're mod 2 in the integers. Alpha to the 4 plops us here. Alpha to the 5 lands us here. Alpha to the 6 lands us here. Alpha to the 7 lands us at 1, which means alpha to the 8 gets us back to where we started. Alpha is equivalent to alpha to the 8. That is not a coincidence that the field was of size 8. So in both of these fields, I just declared that x was going to be our primitive element. Primitive, not like basic, but primitive as in you can build everything off of it. My question to you is, could I have picked a different primitive? Is the primitive for either of these fields unique? Or did I have to pick x?
I don't think you could have picked all of them. Like, I don't think if you picked one, it would work.
Okay, can't pick 1, can't pick 0, but any of the others?
I think so. They're just different parts in the field. They could be named anything else, as you said before.
Right, yeah, that's one way to look at it. Another way is to just like try it, call that one beta, and then I think you end up with this guy being beta squared. So the definition of a primitive element is an element which you raise it to enough powers, you hit every element of the field. Or truly, you get back to 1. So this is beta squared. This one is beta to the 3. Beta to the 4 is the last. Beta to the 5 ends up ending here. Beta to the 6 is there. And beta to the 7 is here, which means this is also beta to the 8. So the important ones is that if we assign the primitive to be x plus 1, then we do indeed get back to 1. And if we raise that primitive to the 8th power, i.e. the field size, we get back to where we started. So the big picture here is that the primitive, I keep saying the primitive element, but it's just a primitive element. Primitive elements are not unique. There might be many in a given field. Okay. Let's see, other factoids. All finite fields have a primitive element. You're guaranteed that based on the way we've defined multiplicative inverses and closure of fields. And so what else can we say? Other important facts. I said all fields, all finite fields have primitive elements. Not plural, have at least one primitive element. And if alpha is a primitive element of the field of size q, then we also call alpha the nth root of unity. Alpha is the nth root of unity, where n is one less than the field size. So for example, taking this relationship, for example, so here q is 8, we have 1 equals alpha to the 7, which means if I raise both sides to the 1/7, then alpha is the 7th root of unity in this field. If I raise 1 to the 1/7 power, then I get a root here. And then what else do we know? So this is identical to saying alpha to the n is always equal to 1 in the field. And if alpha is an nth root of unity, so is alpha to the L, where L is another integer. Why? Because alpha nth root of unity means alpha to the n equals 1. So if I raise this to the L and I raise that to the L, then I also get alpha to the n to the L to the n equals 1 to the L equals 1. So what I'm saying is that all of these field elements then become nth roots of unity in that field, because all of the field elements are gotten to by raising alpha, these primitive elements, to various powers. I don't want to pass this by because I think it's a nice connection to make. Is you've maybe seen this term root of unity before when you start talking about the DFT in 328 or your discrete time classes. So e to the j 2 pi n times k divided by n, this is often called an nth root of unity. And it's the basis for your DFT. So I think pure mathematicians would look at a DFT and see it as an expression of numbers in a finite field of size n. Okay, that gives me 10 minutes to do what I've been building up to for 3 days. Let's talk about Reed-Solomon. And the context I'm going to give you here is Reed-Solomon. If you see Reed-Solomon, I'd like you to think these are non-binary cyclic like linear codes. And the reason we've been doing so much buildup is because of this part, is these are now 9 non-binary codes. They're not just bits. Okay, so the notation is a Reed-Solomon code, uses n code bits to encode k data bits with a minimum distance between code words of the third argument here. So just like before, this is code word length. This is data word length. And then this third parameter is the minimum distance between code words, Hamming distance, right? Minimum number of bit flips required to get from one code word to the next. So a quick callback is if I'm told that the minimum distance between any two code words is 2t plus 1, that means that I can draw a Hamming sphere of radius t around every code word, and I'm guaranteed to not intersect anyone else's Hamming sphere. Which means that in a bubble of radius t around every code word is a unique mapping back to the closest, quote unquote, closest Hamming distance code word. So when you see this, I want you to think this is a t error correcting code. Right, our Hamming 7.4 had a minimum distance of 3, which meant that it was a 1 error correcting code. Okay, so that's the notation. So RS nk 2t plus 1 is generated by the polynomial g of x is equal to x minus alpha to the b times x minus alpha to the b plus 1 dot 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 times x minus alpha to the b plus 2t minus 1. So typically, this is the general form. So typically, you set b to 0. So these b's just go away. But in general, that you can increment b as well. And also typically, we choose 2t plus 1 to be the same as n minus k plus 1. So this looks like it's a 3 degree of freedom system, n and k and t. But once we enforce this, it shrinks back down to a 2 degree of freedom system. And what I mean by that is you can set 2 of 3, n or k or t, and you get the other one from this relationship. Okay, so and alpha, so where I haven't told you what alpha is a primitive element of some finite field of size q. Again, typically q is n plus 1, or another way to say this is that n is q minus 1. So you will see, and this is where the non-binary comes in, is because your g of x polynomial, this generator, has these non-binary things in them, right? The alphas were elements of these abstract fields. They could be 0, they could be 1, but more commonly, well, actually, sorry, if it's a primitive element, it can't be 0, it can't be 1. If it's a primitive element, then it's things like x plus 1, et cetera, et cetera. So the idea is that the alphas aren't binary, but at the end of the day, right, when you say non-binary to a computer person, it ends up being kind of a strange conversation. so for a sidebar, if alpha ends up being, say, x plus 1, then a computer is not going to recognize this as x plus 1. A computer is going to write this as 1, 1, right? At the end of the day, you're really just pulling coefficients here. So let me give you an application example. So I guess some common values would be, say, q is equal to 256, which means that your alpha is a member of a field of size 256. But if alpha is the size of field 256, then that means alpha is representable by a byte, right? If I want to enumerate 256 things, I only need 8 bits. So even though alpha is going to appear as a polynomial, that polynomial will only go up to a power of 7, a degree 7. Okay, so if q is 256, then n would be 255 if we follow this rule. And then the other degree of freedom that you can get is pick this, pick k equal to 223. And this gives a difference is 32 check symbols. Where here I'm using symbols in the field vocabulary rather than in the kind of QPSK digital modulation vocabulary. So since we have picked this as 32 check symbols, what this tells us is that we can correct up to 16 symbol errors per block. So this is important because I'm not talking about bit errors anymore. And so we have to do an extra layer of kind of analysis to understand what this buys us. And actually I'm not going to go into the proof of why this can correct 16 symbol errors, but it has to do with we're doing now parity checks, but parity checks on things that are no longer just bits, parity checks on things that are now multidimensional symbols. And so the idea is that we've expanded our Hamming spheres because we're using things that are in larger spaces, or larger fields, I should say. So let's think about the quote-unquote best case would be we get 16 symbols that are corrupted, but every bit in those symbols are corrupted. So 16 symbols corrupted times 8 bits per symbol means that we can potentially correct 128 bit errors in, well, 255 symbols times 8 bits per symbol in a block of length 2040. Which is pretty good, right? Remember, a Hamming code can correct one error in n bits. So I think it would be an interesting exercise to see what rate Hamming code would you need to accomplish the same kind of bit error performance. But this is best case because it assumes that all of our bits that were corrupted are in clumped symbols, right? This is also why people say that Reed-Solomon codes are great for burst error correction, because if you keep the bits representing each symbol close temporally, right? If you put them all in a line, then if your channel gets clobbered for 8 bits worth of time, then at most that's 2 symbols. Whereas in a Hamming code, you'd be completely SOL. So the worst case would be something like 17-bit errors, but those 17-bit errors spread across 17 different symbols on 17 different symbols. And because you've got 17 symbols in error, this is uncorrectable, because we can only correct up to 16. So this is why it's a bit complicated, is because in some cases, I can correct 128 bits out of 2040, and in other cases, I can't even correct 17 out of 2040 because of the timing of where those bits are located. Okay, so this is kind of live by the sword, die by the sword operation, and it's also why one wouldn't choose to use Reed-Solomon in a very healthy, non-bursty channel. Okay. So then I guess like the last thing I have here is the second worst case, worst minus one, would be 16-bit errors in 16 symbols, which is correctable, which means that I can correct 16 out of 2040. Or I can tolerate 16-bit errors in 2040 total bits. So the range of bit error performances is I can correct any 16 bits out of 2040 bits sent, but there are some cases where I can't correct 17 out of 2040, some cases where I can correct 17 out of 2040, and that whole statement continues up until 128 out of 2040. If I were to have 129 bit errors out of 2040, that would again be uncorrectable, because that would mean it would spill over into a 17th symbol. It would have to. Okay, I think that does it for me. Yeah, I'll pause and I'll hang around here for questions, but we're already over time. So thank you, and I will see you on Friday when we will start talking about convolutional codes.